Hello guys, today we're talking about 2018 AMC10A number 18. So how many non-negative integers can be written in the form that where i's has been between 1, 0, and -1 for 0 is less than or equal to i's less than or equal to 7. So we notice that this is either negative, positive, or 0. And the number of integers that are negative plus the number of integers that are positive plus the number of integers that are 0 is equal to 3 to the 8, because there's 8 slots and there's 3 choices for each of them. So 3 to the 8 is 6561. So we notice that the negative and the positive possibilities are equal. We know this because they're symmetric. For every -1, there's a 1. So all we need to find is the number of zeros, number of values that give us 0. And then we just subtract it from the total and divide it by 2. And conveniently, the only way that we can get 0 in this equation is if every a of I is 0. So that means that we can just do 6561 minus 1, which is 6560. And since there's a positive and a negative, we can do 6560 divided by 2, which is 3280. That's not the answer, because how many non-negative integers? Non-negative. So there's 3280 positive integers, and there's also 0, because 0 is also non-negative, so there's also 1. So our answer is 3281. D. Today we're talking about 2018 AMC10A number 20. A scanning code consists of 7 by 7 grid of squares with some of the square colored black and others colored white. There must be at least one square of each color in this grid of 49 squares. A scanning code is called symmetric if its look does not change when the entire square is rotated by a multiple of 90. Counterclockwise around the center. No one is reflected across a line joining opposite corners or a line joining midpoints at opposite sides. What is the total number of possible symmetric scanning codes? So all 3 of these mini 3x3 squares have to be the same after rotation. We don't have to care about the plus in the middle just yet. So these all have to be the same. So we can start by numbering the sides. 1, 2, 3, 4, 5, 6, 7, 8, 9. After a 90-degree turn, you can turn your head 90 degrees and see that it's 1, 4, 7, 2, 3, 5, 6, 8, 9. After another turn this way, we get 1, 2, 3, 4, 7, 8, 9, 6, 5. One last turn, we get 1, 2, 3, 4, 7, 5, sorry, not 5, 6, 8, 9. And after one more turn, this is what we get. And let's just number the sides D, C, B, and A. And after rotation, B has to be here, here, and here. C, D, C, D, C, D. So let's not worry about the cross in the middle just yet. We don't need to worry about that. So since it's also symmetric when it's reflected across a line joining opposite corners, that means that 2 has to be equal to 4, 3 has to be equal to 7, and 6 has to be equal to 8, or else they won't not be symmetric across opposite sides. So we can modify our graph by, let's just draw a 3x3 square. And this problem is a little tricky, but once you understand the logic, it becomes easy. Sorry, give me a second. So we notice now this graph has to be 1, 2 on both sides, 5, 3, 6, 6, 9. Or in other words, there are 6 distinct numbers here. and they can either be black or white. It doesn't matter. So there's 2 to the 6 ways to order these. And now for the cross in the middle. The cross in the middle, obviously the B has to be same, because after reflected across a line through the middle, they have to be the same. So all of these have to be the same. So there's 4 distinct numbers here. So that's 16. So we have 2 to the 6th times 2 to the 4th. Well, that's not all, because the code cannot be all black or all white. So we have to subtract 2, the case where it's all black, case where it's all white. And this gives us 1022. And that is our answer. Thank you. Hello guys, today I'm talking about the 2018 AMC10A number 21. So which of the following describes a set of values for a for which the curves x squared plus y squared is equal to a squared and y is equal to x squared minus a and the real xy plane intersect at exactly 3 points. So since they intersect, they have to be equal. So we can plug this into this. So by intersect, they mean that for one certain value of x, y, and a, that both these equations will be satisfied. So if we plug in the second equation into the first equation, we get x squared plus x squared minus a squared equal to a squared. So after simplification, we get x squared plus, sorry, not plus, after simplification, we can factor in x squared. We get x squared 1 plus x squared minus 2a is equal to 0. So x is equal to 0. So either x squared is equal to 0 or x squared minus 2a plus 1 is equal to 0. So I'm going to rewrite this. It was a little bit bad handwriting. So this is when x is equal to 0. So when this happens, x squared is equal to 2a minus 1. So x is equal to plus minus square root of 2a minus 1. So since x is a real number, 2a minus 1 has to be non-negative. Because if it's a negative number, this would be I, and x will not be a real number in the real xy plane. So 2a has to be greater than or equal to 0. So 2a is greater than or equal to 1. A is greater than or equal to 1/2. And that is our solution. Thank you. Hey guys, today we're talking about the 2018 AMC10A number 823. Farmer Pythagoras has a field in the shape of a right triangle. As the graph shows, the right triangle's legs have lengths 3 and 4 units. In the corner, where the sides meet at a right angle, he leaves a small unplanted square S, so that from the air it looks like a right angle symbol. The rest of the field is planted. The short distance from the S to the highline is 2 inches. What is the fraction of the field planted? So we can draw a line from here to the axes and here. So what this does is splits this triangle into 3 areas. Area 1, Area 2, and Area 3. And the area is as follows. So this is a perpendicular because the closest area is this perpendicular bisector. So the area of 1 is just 5 times 2 over 2, because the base, the height is 2 over 2. Area of 2 is 3 times the height is x over 2. And the height of A3 is same as A2, but with a different base. So adding these up, we get 5 plus 7x over 2 is equal to the area, which is 6. So 7x is equal to 2. So x is equal to 2 over 7. Since x equals 2 over 7, we've pretty much solved the problem. The rest of the field is unplanted. The rest of the field is planted. So the unplanted part of the field is 4 over 49. So we get 6 subtracted this, and this gives us 290 over 49. And we have to subtract, since we have to find the fraction of the field, this divided by 6, and this gives us 145 over 147. And that is our answer, D. Thank you for watching. Hello guys, today we're talking about 2018 AMC10A number 25. So for a positive integer n and non-zero digits a, b, and c, let a of n be the n-digit integer, each of whose digits is equal to a. Let b of n be the n-digit integer, each of whose digits is equal to b. And let c of n be the 2n-digit, not n-digit integer, each of whose digits is equal to c. What is the greatest possible value of a plus b plus c for which there are at least two values of n such that cn minus bn is equal to an squared? So we can rewrite a of n at just a times 1, 1, 1, 1, 1, because all of the digits are equal to a, and there's n digits. And we can obviously duplicate this for all the other ones. So I'm just going to do real quick 2n digits. Obviously, these are not a. So we get c of n is equal to c times b of n. So equating these, we get a times 1 plus 10 plus dot 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 to 10 to the n minus 1th power. And this is just a geometric sequence. We can simplify this to a times 10 to the n minus 1 over 9. And same with these ones. So what we have now is we have a times, so we have a squared times 10n minus 1 over 9 squared is equal to c times 10 2n minus 1 over 9 minus b times 10n minus 1 over 9. So we can start equating these and simplifying. So we can multiply 9 on both sides. We get 9c is equal to, 9c times 10 2n minus 1 minus 9b times 10n minus 1 is equal to a squared times 10n minus 1 squared. We can also divide 10 to the n minus 1 squared because this is just difference of squares. This is just 10n minus 1 times 10n plus 1. So dividing a 10n minus 1 on both sides, this becomes this. So we get 9, and then now we can start doing 9c times 10n plus 9c minus 9b is equal to a squared times 10n minus a squared. So adding everything to one side, let me add another page. Adding everything to one side, we get 9c minus a squared times 10 to the n is equal to 9b minus 9c minus a squared. So since n is not a constant, we have to make sure that these are equal for every possible n. And the only way we can do this is that if both sides are equal to 0. So this has to be equal to 0, and this has to be equal to 0. So in this case, 9c is equal to a squared. So c is equal to a squared over 9. And in this case, we can do 9b minus, 9c is a squared, so minus 2a squared is equal to 0. So b is equal to 2a squared over 9. So what we have, since we're trying to find A plus B plus C, right here, we can simplify this. We go into A plus A 2A squared over 9 plus A squared over 9. So it's just A plus A squared over 3. It's just simplifications. So now we can just test out some values because A is a digit. So A can not be from 1 to 10, it has to be from 1 to 9. And it has to be divisible by 3 because B and C have to be integers because they're also other digits. So we test out 9. For 9, if A is 9, then B is 18. And obviously that can't work because B has to be a digit. If A is 6, B is, well, 36 divided by 9 is 4, so B is 8. And C is B over 2, so C is 4. So this actually works. So we're trying to find the greatest possible value for A plus B plus C. So we get 6 plus 8 plus 4, and that gives us 18. And that is one of our answers. Thank you.